Hello, we're going to walk through a few of the quest problems for the Newton Law and Forces quest. And I want to walk you through some of these, give you a couple pointers, and not work them out to completion, but get you started and so you can work through those at your own. The first thing that I want to focus on with 1 and 2, both of these are talking about the same problem where you have a force of 76 newtons. They're saying that it's pulling with 46 degrees to the horizontal, and there's an x component and a y component. Right away, when I see these problems, I'm going to draw a sketch with a triangle because I know I need to use my right angle trig and my SOHCAHTOA to figure this out. So the force was 76 newtons, and they're giving us where the angle is by telling us this is 46 degrees above horizontal. So I'm going to draw horizontal in here. And that 46 degrees would be right here. It's above the horizontal. And then I want to form the legs of that right triangle. So I'm going to have one side here that makes a right triangle with the horizontal and another side right here. Okay, so those two vectors are the components. Now, obviously, the purple one that I just drew in, that's moving horizontally, so we call that the x component. And the green one is moving vertically. We call that the y component. Again, you'll use your SOHCAHTOA in order to figure out what the answer is for those components of x and y using the hypotenuse of 76 for your problem there. All right, the other question that I wanted to run through was number 4. And for number 4, we have this otter sliding down, and this one is a throwback to some things that we've done before with the kinematics. So yes, we are going to use F equals ma, where we're solving for force. They give us the mass, but they don't tell us the acceleration. Instead, they give us a distance and a time. So first convert your centimeters to meters, and then we can find one of our old equations for displacement that involves acceleration. So one of those kinematic equations. Now in this equation, the initial velocity is 0. So this term will go away. So then the distance is just equal to 1/2 times acceleration times time squared. You can then substitute in the distance and the time, solve for acceleration, and then that gets plugged back into this equation here to find force. All right, so that should get you started on that one. Number 5, very similarly, we're going to use those two equations again, knowing that we want to solve for ultimately the distance traveled, but they're giving enough information so that we can, in this case, solve for acceleration first and then plug that acceleration back into this equation to solve for the distance traveled. Okay, so those are those types of things. I do want to make a really important point. Weight is not the same as mass, and weight for these questions is a force. So the force of weight is equal to an object's mass times the acceleration of gravity. And it is measured in newtons. Weight is a force. And so we need to include it in free body diagrams, and we need to use it when we're calculating these other quantities. So really big key idea there. All right, the other question that I wanted to tie in is like number 10 is when you take a look at these questions that involve multiple forces and they're talking about the resultant force here, again, think right triangles. So how can I combine these forces, the two forces that are acting vertically and the two forces that are acting horizontally, how can I combine those to create an overall horizontal force and an overall vertical force that makes a right triangle so I can solve for the resultant, which is the hypotenuse. So resultant is always going to be talking about that hypotenuse force for the right triangle, okay? And kind of be thinking through those when you see those words. Those are clues of what to think about. All right, number 12. This is another really core kind of question where we need to realize a couple things, and a free body diagram helps you explore the forces. So it says we have a bucket of water. They give us the mass of the bucket raised from a well by a rope. Okay, so if this is the bucket, there is a force of weight pulling down on the bucket. It is not 4.9 kilograms. The weight is a force. So you take 4.9, the mass, times 9.8, acceleration of gravity. That becomes your weight force. And then it says there's an upward acceleration of the bucket as 3.1 meters per second. Find the force exerted by the rope. So they're telling us that as these two forces combine together, the pull or the applied force from the rope minus the weight force, because they're in opposite direction, will equal a net force. And that net force is giving us the acceleration of 3.1 meters per second squared. Therefore, I need to subtract applied minus weight is equal to mass times acceleration of the bucket. All right, from there, you can substitute in knowing that weight is mass times gravity. They give you the mass, you know what G is, and subtract to find out that final applied force. Key idea is here that by drawing your free body diagram, you notice there are really two forces acting on that bucket. They combine together to make the net force. So you have to build that net force equation. All right, number 13, consider the 65 Newton weight held by two cables. Left hand is horizontal. Oh, yes. So again, when I see angles, like here, this 53 degrees, I'm automatically thinking, how can I make this into a right triangle? What am I going to use for the legs of that right triangle? And what makes sense, all right? So right away, one part of that right triangle is going to be a vertical piece right here. All right, that is exactly equal to the downward piece in the vertical direction, the 65 newtons. I know that because this is it's stationary. All the forces are in balance, they're in equilibrium. So therefore, this has to be 65 newtons pointing straight up. We can then use our SOHCAHTOA to figure out what is the horizontal force. What is this force right here? And we can use that because we know the angle and we know one of the sides. And so therefore we can figure out what that other force is using our trig, using our SOHCAHTOA. All right. So whenever I see angles, I want to make it into a right triangle and then use my SOHCAHTOA from there. The horizontal cable, again, looking at this picture, I have two of these arrows. I have if I draw my free body diagram, I have a horizontal piece here, a force that we don't know of yet, but we can find out. And I have another force going in this direction. All right. Because they are in equilibrium, these two forces would equal each other. So this tension force that's pulling to the left must equal this force that we just calculated is pulling to the right. All right. Otherwise, there would be an acceleration. There'd be a net force, which there is not. They're at rest. It's the equilibrium. All right. So therefore, we can use our trig again to